next type of classification on the basis of direction of flow of water is the axial flow turbine. So here what happens is you have a bulb like this and you have some fans connected like this. As it is getting rotated, this will be rotating in this direction. So it will be rotating like this. So this will be having a rotation in this direction. As it is getting rotated, the motion of liquid will be in this direction. The motion of liquid will be in this direction. So here what happens is, this is your axis of rotation. This is the axis of rotation, and here the liquid flow is not tangential, it's not radial. What happens is that it is rotating like this, it is flowing in the direction parallel to the axis of rotation. So that's why this type of turbine is called as an axial flow turbine. And the example for axial flow turbine is Kaplan turbine and propeller turbine. So the example is Kaplan and propeller turbine. Kaplan and propeller turbines are example for axial flow turbine. This is how it happens. As it is rotating, the flow velocity, the flow direction will be parallel to the axis of rotation.
Kaplan turbines are suitable for power extraction when water energy is available at low head and high flow rate, which means they are suitable for operation when water is stored in a big reservoir at a relatively shallow altitude. In Kaplan turbine, flow is entered through a spiral casing. Decreasing area of casing makes sure that flow is entered to the central portion, almost at uniform velocity, throughout the perimeter. Water after crossing the guide vanes, passes over the runner. Finally it leaves, through a draft tube. Most important part of Kaplan turbine is its runner. Cross-section of runner blade will have a curved shape. When water flows over it, it will induce a lift force due to airfoil effect. Tangential component of lift force will make the runner rotate. This rotation is transferred to a generator, for electricity production. Kaplan turbines are axial flow machines, where absolute velocity of flow is parallel to axis of turbine. Water is precisely made to pass through runner blades, with help of a shroud. Power demand may fluctuate over time. A governing mechanism, which controls position of guide vanes, is used to control water flow rate. This can meet for varying power demand. Blades of Kaplan turbine are designed to operate under a wide range of operating conditions. A rotating blade experiences relative velocity of flow. The fundamental thing in blade design is relative velocity of fluid flow should be at optimum angle of attack at all cross sections. Even though absolute velocity is axial, relative velocity will be inclined, depending upon blade velocity. Inclination of relative velocity increases, as we move from root to tip, due to increasing blade velocity. There should be continuous twist in blade, from root to tip, so that at every cross-section the angle of attack is optimum. With varying flow condition, relative velocity will change drastically. Kaplan turbine blades are adjustable. When flow rate is high, relative velocity of flow will be more axial, so blade should pitch vertically. If flow rate is low, relative velocity of flow is more tangential, so blades are pitched in tangential direction. In short, pitching action of blade makes sure that blade is still in optimum angle of attack, even under varying flow. Apart from controlling the flow rate, guide vanes have got one more function. They help in controlling swirl of flow. If guide vanes were not present, the flow would be highly swirling in nature, due to its tangential entry. Such a flow would reduce performance of turbine drastically, due to its poor angle of attack. So guide vanes control swirl of flow, for optimum angle of attack.
So coming to the last type of turbine in the type of direction based on classification based on the direction of flow of water. So we have the mixed flow turbine. Mixed flow turbine will be having both axial flow as well as radial flow. So it's a combination of axial and radial flow turbine. And the type of turbine which has both this axial and radial flow turbine is your Francis turbine. Your Francis turbine will be an example for mixed flow turbine, and we'll be learning about Francis turbine in detail in the coming lectures.
Francis turbines are the most preferred hydraulic turbines. It contributes about 60% of the global hydropower capacity, mainly because it can work efficiently under a wide range of operating conditions. Most important part of Francis turbine is its runner. It is fitted with a collection of complex-shaped blades. In runner, water is entered radially and leaves axially. During the course of flow, water glides over runner blades. Francis turbine blades are specially shaped. You can note that blades are having thin airfoil cross-section. So when water flows over it, a low pressure will be produced on one side and high pressure on the other side. This will result in a lift force. You can also note one more peculiar thing about the blade. It is having a bucket kind of shape towards the outlet. So water will hit and produce an impulse force before leaving the runner. Both impulse force and lift force will make the runner rotate. So Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. Thus, as water flows over runner blades, both its kinetic and pressure energy will come down. Since flow is entering radially and leaves axially, they are also called mixed flow turbine. Runner is connected to generator via a shaft for electricity production. This arrangement is fitted inside a spiral casing. Flow is entered via an inlet nozzle. Flow rate of water will get reduced along length of casing, since water is drawn into the runner. But decreasing area of spiral casing will make sure that flow is entered to runner region almost at uniform velocity. Stay vanes and guide vanes are fitted at entrance of runner. The basic purpose of them is to convert one part of pressure energy to kinetic energy. Flow which is coming from the casing meets stay vanes, they are fixed. Stay vanes steers the flow towards the runner section, thus it reduces swirl of inlet flow. Demand for power may vary over time. The guide vane mechanism is used to control water flow rate and makes sure that power production is synchronized with power demand. Apart from controlling flow rate, guide vanes also control flow angle to inlet portion of runner blade. Thus, guide vanes make sure that inlet flow angle is at optimum angle of attack for maximum power extraction from fluid.